The next thing we're going to talk about is geometric isomers called cis and trans. This is also a type of stereoisomer, all right, because they differ in how they look in 3 dimensions. Okay, so cis and trans. So remember, we have restricted rotation around a double bond. If this was not a double bond, we would really not have cis and trans. If this was a single bond, these can freely rotate around each other, and I don't have this. But because this is locked in this position, notice there are 2 different types of molecules. They both are basically the same compound. They are 4 carbons with a double bond in the middle. 4 carbons, right? 1, 2, 3, 4 with a double bond in the middle. 1, 2, 3, 4 with double bond in the middle. But notice one of them have the methyl groups on the same side of the double bond. So imagine my double bond as a plane. So imagine this is the plane. These 2 methyl groups are on the same side, where in this case your 2 methyl groups are on opposite sides. And remember, there is no rotation around the double bond. Okay, let's erase these. So the one where the 2 groups are on the same side, it's called the cis isomer. All right, cis for same, that's kind of how to remember it. And the opposite are trans, meaning opposite of each other. Okay, so these are isomers, okay, but these are stereoisomers because they're basically the same molecule. It's not a constitutional isomer because, yes, they have the same formula, but they are basically the same compound. They just are different in 3 dimensions. This compound is a constitutional isomer because your double bond now is on the first 2 carbons. This is not the same molecule as this. And notice I do not have cis and trans here because this carbon right here has 2 of the same groups. You have to have 2 different groups. Notice I have 2 of the same groups. It doesn't matter which side the hydrogens are on, it's the same molecule. So you don't have a cis and trans on that molecule, but you do because you have non-hydrogen groups in these spots. Okay? So stereoisomers are compounds with the atoms bonded in the same order, but their atoms have different orientation in space. Cis and trans are examples of geometric stereoisomers. I rarely use this term geometric. I prefer stereoisomers, just stereoisomers. Geometric starts getting a little bit more detail oriented, and we don't have to worry about it because it's really the only example of a geometric isomer. So if you just want to know what a stereoisomer, I'm fine with that. All right, they occur when there's a double bond, or if you do not have free rotation. We will see examples where you have a single bond, but it's a cyclical compound, and you don't have free rotation, but you still have cis and trans. Since there's no free rotation along the the carbon-carbon double bond, the groups of these carbons can point in different places in space. All right, here's a hint. If one of the double bonded carbons identical groups on one of the double bonds implies no cis and trans. That's what I just said. If you have 2 of the same groups on the one carbon, you cannot have cis and trans. Okay, notice here I also have the same groups. There is no cis and trans. If one of these was a hydrogen or an oxygen or a nitrogen or something different, then you would have cis and trans. All right, dipoles, polarity, determining if your molecule is polar or nonpolar. That's kind of what we're going to do next. And this is using what we learned about electronegativity and bond polarity. Okay, so increasing polarity. You increase polarity as you attach a more electronegative atom to it, and it becomes more and more ionic. So here I have 2 of the same atoms, so I have basically a nonpolar bond. I add a nitrogen, which is slightly more electronegative than carbon, an oxygen, more electronegative than nitrogen, and now chlorine, which is way more electronegative than an oxygen or nitrogen. Then you have the other extreme, which is ionic. Now you have things which completely rip the electrons away. So it's kind of like a little bit pulling electrons away, a little bit more, a lot more. Now the chlorine just ripped the electron away completely from the nitrogen, and that's why it now has a plus charge. Okay, so dipole moments are due to the difference in electronegativities. These arrows kind of show that. Okay, they depend on the amount of charge and the distance of separation. I kind of want to show you this. These arrows aren't correct, not completely. You notice that the arrows are equal in size. Well, if you're going to do a dipole arrow, you kind of want to show the size of it as well. So technically, the dipole for the nitrogen would be like that. The oxygen would be a little bit bigger because the oxygen is more electronegative. And then finally, the chlorine, which is much more electronegative, would be a bigger arrow. Okay, so the dipole both have the direction as well as like the size of it. Is it more electronegative or less electronegative? So that's bond dipole moments. This is molecular dipole moment. This is your molecule now polar or nonpolar? Okay, and what you need to do is, in order to find the molecular dipole moment, you sum all the atomic dipoles. Okay, sum all of the atomic dipoles. Okay, so that means I'm going to take the dipole of this carbon hydrogen, which virtually is 0. I know they put little arrows in here. I want you to know that carbon and hydrogen really don't have a dipole. Okay, I don't like how your book does that. They do have a very, very slight dipole, but for our class, we're going to assume it has 0 dipole. So basically, this molecule, I have a 0 dipole here, 0 here, 0 here, but then I have a dipole right here between the carbon and chlorine. So I add up all the dipoles, all the arrows. All right, so I don't 0, 0, 0 plus a dipole moving that direction. I have a dipole of that way. That's kind of what it's showing you, a sum of a dipole. Okay, and again, I'm going to cancel this out. Now notice I have a dipole going that way, a dipole going this way, and a dipole that's going that way. If I were to add these up, so this is like in physics, for anyone that's done vector analysis, this is the same as vector analysis. Some of you have done it, some of you have not done it. It's very simple. Imagine I have a particle, and I move it this direction and that direction at the same time. Where does my particle move? So if I'm going to move it this way and that way, all at the same amount and at speed and everything, what's my overall direction of the particle? Well, the overall direction is the particle is going 445 degrees. So that's where the particle is going. So if I take a particle and move it this way, oops, sorry. If I move it this way and move it that way all at the same time, it's going to go that way. If I have a particle and I move it this way equally as the same amount as that way, where's my particle going? It's not going to go anywhere, right? Because if I'm pulling one way and the other way at the same time, it doesn't do anything. Okay, so that's what we're talking about. So when you have a molecule, you have to know the geometry, and you add up all of the dipoles. So this vector plus that vector equals, an overall way of that way. Okay, here's a really good example. All right, here I have a carbon with 4 chlorines, all pulling equal opposite ways. What's my dipole? My dipole is 0. Okay, so this is a non-polar molecule. All right, because everything is being pulled. All right, even on a double bond, again, we're going to ignore the hydrogens. But I mean, you see how small that they're drawing it. Let's just assume it's 0. It makes life so much easier. So bromine's pulling this way at this angle, at that angle. So if you kind of think about it, I have 2 angles, so we're going that way. Okay, so that's how you can determine if your molecule has a dipole or not. So the molecular dipole moment is the vector sum of the bond dipole moments. That's I said the atomic dipoles, it's of the atoms, but you can think of it as each individual bond. It's probably a better way of defining it. Depends on bond polarity and bond angles, so that's important. You need to know the geometry as long as your bond angles. And lone pairs also do contribute. They don't contribute as much, but they do still contribute. Here's an example. You can actually ignore the lone pairs and you'll still get the correct answer. But here's examples where your nitrogen is pulling and then your lone pair is pulling on top of it. Here, each of your lone pairs are pulling this way. Again, you have an overall dipole. It's basically saying this oxygen here is so much electronegative than everything here. It's just going to pull all the electrons towards it. All right, and the same thing for the acetonitrile. Intermolecular forces. This is important. You have definitely learned this. This really kind of explains a lot about a molecule. If you look at a molecule, you can look at the type of intermolecular forces it has based on the structure. you can determine a lot of its properties. You can determine if it's going to have a high boiling point or a low boiling point, a high freezing point, a low freezing point, if it's going to be soluble in water or if it's not going to be soluble in water. There's a lot of things that you can get by just looking at the intermolecular forces of a compound. Okay, these tell you the strength of attractions between molecules. Okay, they influence the melting, the boiling point, and the solubility. I basically just said that without even knowing that that was next on the slide. Classification of attractive forces. There are three types. There are dipole-dipole forces, London dispersion forces, and then there's hydrogen bonding in a molecule. Hydrogen bonding is a type of a dipole-dipole force. Okay, so it's kind of a special type of a dipole-dipole. They're very strong interactions. What we're talking about, just to make sure you know what we're talking about, we're talking about interactions between molecules. So imagine I have one molecule, let's say water. This water molecule is attracted to another water molecule. Okay, it's this attraction that we're talking about. That's the intermolecular force. Obviously, atoms are attracted towards each other through covalent and ionic bonds. But molecules are attracted to other molecules through these other special kind of forces, and they are either a dipole-dipole force, London dispersion, or a hydrogen bond. In this case, water is attracted towards a hydrogen bond. So let's go through all these three again so that you remember. I'm going to start with London dispersion because it's the weakest of all of the forces. It's the weakest because it is between nonpolar molecules. If you have a nonpolar molecule, that you have a London dispersion force. Okay, this is a type of a van der Waals force. A lot of people think that London dispersion and van der Waals forces are the same thing. Well, they kind of are. It's more like, you know, it's like a category. There are lots of different types of van der Waals forces, and this is one type of a van der Waals force. It's the only type that we're going to talk about. So if you want to call it a van der Waals force, that's fine too. It's a temporary dipole moment in a molecule that can induce a temporary dipole moment in a nearby molecule. I kind of think about it like, imagine you have a bucket of water and you shake that bucket, the water kind of sloshes back and forth. That's kind of what the electron cloud is doing on a nonpolar molecule. The electron cloud is kind of waving back and forth and back and forth. It's not really on any particular atom. Okay? So once you form a more negative side of a molecule, that repels electrons on another molecule, creating more of a positive end, which then creates a temporary London dispersion force. All right, so an attractive dipole-dipole interaction results just for a fraction of a second. Okay, the main force is between nonpolar molecules. Larger atoms are more polarizable. That means the electrons are able to waft back and forth. It's like having a bigger container for the water. Okay, so just imagine the molecule is kind of sloshing. I gotta get. Oops, sorry about that. So the electrons are swifting back and forth and back and forth, and if you form more of a negative side on this molecule, that creates a more of a positive end on this one, because this minus repels the electrons, so you have a slight attraction between that negative end and the positive end. Okay, so here's kind of an example, and then eventually the electrons will shift, and this becomes more negative, so that will then break that interaction, and you no longer have an interaction anymore. Okay, here's kind of the effect. All right. So these are all nonpolar. Remember I told you carbon and hydrogen are nonpolar bonds, so basically this is a nonpolar molecule. We're going to look at the boiling points, the difference between a straight chain molecule as you get one branching group or if you get two branching groups. Okay? The less or the more branching you get, your boiling points go lower, meaning the interactions are weaker. All right? Your London forces are weaker as you branch. Okay? And the reason is because you now have less forces between them. Okay? So here I have a straight chain. If I have another straight chain near it, I have an interaction here, interaction here, interaction here, interaction here, interaction here. These can kind of, it's kind of like a packing effect. These straight molecules are able to pack on top of each other. If you get a branching group, you no longer have, so notice I have like 1, 2, 3, 4, 5 interactions. If you have it branched, you now have less amount of interactions. Interact, 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 interact. So you no longer have an interaction of these other carbons. And then if you get even more branched, you have even less of an interaction. You only have 3 interactions. So it's more of like a ball. It's like these balls in this case, imagine that as a ball, are interacting. It's not like these straight sheets. Okay? So that's kind of a great way to actually explain why you have less interactions. So your boiling points and all the melting points are lower. So long chain isomers has the greatest surface area, which is exactly what I was saying here. So the boiling points are higher. As your branching increases, you get less surface area, it becomes more of a sphere. The most highly branched neopentane has the smallest surface area, therefore it has the lowest boiling point. So by looking at molecules, you can kind of determine if the boiling point is going to be lower or higher. Okay?